Questions? So I haven't even thought about the exam, but what I will do is put 4 problems. So, and I have 3 chapters. So I'm going to cover all chapters. So what I haven't decided is which chapter I'm going to put 2 problems on. So most likely chapter 23, I can put 2 problems. And ultimately, I mean, why do you calculate electric fields? So that you can calculate forces exerted by those electric fields on charged particles placed on that electric field. Why would you want another force? Because that force will determine what the acceleration of the thing is going to be. Why are you interested in the acceleration? Well, maybe the thing is going to move. And if it moves, what's up? Well, I want to know maybe how long it's going to take it to go from here to there, what velocity it's going to have over there. So expect a problem with a point charge moving. So maybe from chapter 23, I'll put a problem like the one that we started with today. You know, something is released from rest or whatever, blah, 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 right? Something similar to that, right? But a charged particle moving in the presence of other charged particles, right? And then we did what? Electric fields calculations from chapter 21. We did Gauss's law calculations in chapter 22. And then another potential difference calculation, voltage, potential difference calculation in chapter 23. Plus another one with a charge moving. So that's probably a good set of 4 problems that you could expect.
Can you go over chapter 23, homework problem number 8? How to set it up?
In Corral or the other one?
Coral, whatever.
Oh, Coral. I say Corral, but I don't know. It's probably Coral, right? Anyway. Chapter 20, so it would be this one. 23, did you say?
Yes.
So, is it this one?
Yes.
So it says 2 large charged plates with charge density plus and minus 30 microcoulombs per meter square face each other with a separation of 5 millimeters. Okay, so let me start with that. So we have one over here and another one over here. And I'm going to make this plus and minus. Right? And this is plus sigma, which is 30 microcoulombs per meter square. So this is 30 times 10 to the minus 6 coulombs per meter squared. And the charge of this one is minus 30 times 10 to the minus 6 coulombs per meter squared. Right? And they're separated by a distance. Was it 1 millimeter? 5 millimeters. So this is 5 times 10 to the minus 3 meters. Right?
What does the negative plate is grounded and defined as 0 potential mean?
So that means that if the potential over here is 0, oh, the negative one is the one that's grounded? Okay? That means that the potential of this plate, the potential of the negative plate is 0. Just quickly. Let me change something just really quickly, right? Well, before I change it, is there an electric field in here? Is there an electric field here, yes or no?
Yes.
Yes. Which is it pointing?
To the right.
Oh, sorry.
Which way is the electric field pointing?
To the right.
Away from the positive towards the negative. Away from this towards that. Not to the left. Right? And what's the magnitude of it? This is a set of very large plates. Sigma, which is that number, over epsilon naught, right? Yes?
How do you know, is it always electric field going to the negative?
Always. That's the very first thing we learn in chapter 21. Away from the positive charge, towards the negative charge. Always. Always. Now, suppose, just for the sake of argument, right? I haven't evaluated these numbers and so on. Suppose you get that this electric field, you work it out that you get 10 volts per meter. And suppose this distance, right? This distance is 2 meters. What will be the potential of this plate? 20 volts. Exactly. That's a 1-2 second type of question. Why not minus 20? So if you go away not away, but in the opposite direction of the electric field, the potential gets bigger. So, and for every meter that you walk, it's going to change by 10 because this is 0. 1 meter over here is going to be 10 volts per meter, and over here 20 volts per meter. I mean the potential 10 volts, 20 volts. This electric field is uniform, so I can do that. Those problems that you can do in 1 second in your head, 1-2 seconds. Remember we did those. That's what this problem is about, kind of. Except that, okay, 10 5 times 10 to the minus 3, and then I don't know what you get when you do that one, but just if you had the numbers, right? So if this distance were 2 meters and this happened to be 10 volts per meter, the potential there is 0. 1 meter away, right? If they ask me, the potential there will be 10 volts. And, over here, the potential will be, well, it'll change by another 10 during that 1 meter, so it should be 20 volts. So maybe one of the questions is, what's the potential of this plate? Maybe, I don't know, let's see. Find the electric potential at a location 2 millimeters from the negative plate. Do they want 2 answers over here? So find the electric potential at a location 2 millimeters from the negative plate, which is what, 7 millimeters from the positive plate? Are they separated by 9 millimeters?
Wouldn't it be
Or
like
how do you-
Wouldn't it be 2 millimeters to the right of the negative?
Oh, this is 5. Okay, so it would be here, right?
Yeah.
So this is, okay, so that's 5 millimeters and that's 2 millimeters. What's the electric field in this region?
Sigma over 2 epsilon naught.
We're outside the
Oh,
plate.
yes.
What is it? What is the electric field in this region? Outside a set of oppositely charged plates. It's 0. And if the electric field is 0, what can you say about the electric potential? It's constant. Right? Right? So E is, minus dV dx, right? If this is 0, then V has to be constant. So what is the potential over here? What is it? It's going to be the same value there, here, there. It's going to be the same value. Let me give you a hint. Same as that. It's 0. What will be the potential given these numbers? The 1, the this, the that. What will be the potential over here? What is it? 20 volts. What is it over here? It's the same as this because the potential has to be constant in this region, right? Because this is 0. So this is 20 volts. What about over here? 20 volts. What about over here? 20 volts. Right? If the electric field is zero over some region, the potential is constant. Just like if the acceleration is zero, the velocity is constant. I kind of used them as an analogy a little while ago, but that's really the connection, right? I mean, yes, potential and electric fields are related by a derivative with respect to a space variable. In the case of acceleration and velocity, they're related by a derivative with respect to a time variable, right? Acceleration is dv dt. This is dv dx, and there's a minus sign in there to take care of directions, right? The other difference is that we're relating a scalar function to a vector function. So that's why this is, this is the gradient. In the case of velocity and acceleration, velocity is a vector, acceleration is also a vector, right? So you don't need a gradient. It's just dv dt. But maybe I shouldn't call it constant. Maybe that's bad. I mean, I prefer to actually call it uniform. Because constant means, really, what constant really means is not changing as time goes on. It's the same now as 2 seconds later, as 1 hour later. That's what constant is. Uniform means the same value at any one time in space. So it's better than saying that this is a constant. Better to say uniform. Just like the electric field over here is uniform. If this happens to be 10 volts per meter here, to the right it'll be 10 volts per meter, to the right 10 volts per meter, to the right 10 volts per meter, to the right. That's uniform. The gravitational field in this room, no matter where I ask you, what is the gravitational field generated by the Earth? It's 9.9 meters per second squared down. Over here, 9.9 meters per second squared down. 9.9 meters per second squared down. 9.9 meters per second. So it's uniform. Now, because now it's 9.9 meters per second squared down, and 9.9 meters per second squared down, it's also constant, because it isn't changing as time goes on. Yes? So it looks like this problem is one where there's a lot of concepts associated with it, right? They tell you the potential on this plate is zero. Over here, outside the plates, if you remember, we did Gauss's law for one sheet, and then we did it for the oppositely charged sheet. It shows up so much that that's a problem that is good to remember. The electric field outside the two sheets is zero. The electric field is zero. The electric field between them is something, always pointing from positive to negative. Because the electric field here is equal to something, right? As you move from one plate to the other, the potential is going to change. It's like if the acceleration is something, the velocity is going to change as time goes on, right? But in this case, the electric field is something, so the potential is going to change as you move in space. And we learned that if you move opposite to the electric field, the potential gets bigger. If you go in the same direction as the electric field, the potential gets smaller. In this region, everywhere in here, the electric field is zero. That doesn't mean the potential is zero. It means that the potential is the same, because you were told that it was zero over here, it's going to be zero over there as well. In this region, the electric field is zero. So that doesn't mean that the potential is zero. It means that the potential is the same everywhere in there. It's uniform. And because if we had the 10, these are the easier numbers so that we have this discussion, if this is 20 volts, then it will be 20 volts everywhere in here. So, zero electric field means that the electric potential is the same in that region of space. Whatever it is, it could be 0, 0, 0, 0, it could be 20, 20, 20, 20, 20, 20, 20 volts. Everywhere in space. That's like if the acceleration of a particle is 0, that means that the velocity of the particle is constant. In that case, it's not in space, but as time goes on. And now if the velocity of the particle is 0, then the velocity will stay at 0. The particle will be at rest and remain at rest. But if the acceleration is 0 and the particle is moving, maybe 20 meters per second, it will keep on moving at 20 meters per second. As time goes on, it will stay the same in the same direction. So I don't know if you can see the connection, or if I confused you even more. Sorry. But that's one way to think about them. So electric fields are not the same thing as electric potentials. One of them is a vector quantity, the other one is a scalar quantity. Right? One of them has direction, the other one doesn't. Right? And if the electric field is 0, it says something about, in some region of space, it says something about the electric potential in that region. All you know is that it's the same everywhere in that space, where the electric field is 0. Like over here, since the electric field in this region is 0, the potential would be 0, 0, 0, 0, 0, 0, 0, the same in space, uniform. And because the electric field here is 0, it doesn't mean that the potential here is 0. It means that the potential here is, well, it's going to be here. If it's 20 volts, it'll be 20, 20, 20, 20, 20, 20, 20. Yes? So the first question is, find the electric potential at a location, so that's outside the place. What should be? 0, and I guess they want volts then, maybe capital V. So 0, capital V. Because if they want units, then capital V. And hopefully they have the right answer. Find the electric potential at a location 2 meters from the negative plate, but now 3 meters from the positive plate. Oh, this is fun. Let's see if we have these numbers. What would it be? So, suppose this were, well, suppose this is 10 volts per meter, and suppose this distance is 5 meters. Or actually, yeah, okay, 5 meters, right? So what do they want? Something like 2 millimeters and then 3. So what would it be here? So that this is 2 meters and this is 3 meters. What would the potential here be equal to? If it's going to change from 0 to 20. Actually, I made this now 5, right? So that's 5 units. This would be 50 now. What would it be over here? What would it be? 20 volts, right? At any other point, so it's kind of easy to do with these numbers, but these other ones we gotta work it out. So let's work it out. So do I expect a positive answer for the potential here or negative? Positive because it's 0 over there, and if I walk in the opposite direction of the electric field, it gets bigger. Well, if you start at 0 and it gets bigger, you go to the positive values, right? So the answer has to be positive, not negative. So let's calculate the electric field. I mean, let's actually get a number. It would be sigma over epsilon naught. So,
Thank you.
So the electric field, let me get rid of this also. So I can actually use this. So the electric field is what? It's sigma over epsilon naught. So that would be 30 times 10 to the minus 6 divided by epsilon naught, which is 8.85 times 10 to the, somehow that rings a bell, I think. And this would be meters per kilometer. And it's, to the right. So that's 30 million divided by 8.85, so it's like 3 point something, 3.5 billion, something like that, around there.
3.39.
3.39? So I would keep quite a few decimal places, but for now, let's just say 3.39 times 10 to the 6.
Yes.
Right. All right, let's say that's it. Or maybe I'll just do that, right?
Sorry, 3.39. 3.39.
Oh, 39, not 99. Okay. Thank you. So if the potential here is 0, which is what they said, right? You want to know the potential here at a distance of, what was it, 2 millimeters? So that's 0.02, actually 0.002 meters, or, 2 millimeters is 2 times 10 to the minus 3 meters, right? That's the 2 millimeters. So if I think of this distance as d1, for example, then I can do this calculation. Delta V, the potential difference between those 2 points, is just going to be E times D, right? So this would be 3.39 times 10 to the 6. And that distance is 2 times 10 to the minus 3. And this is going to be in volts. So that's going to be the difference in potential. Like, you get a number in your calculator, and that'll be the difference in potential between these 2 points. But because this is 0, the potential here will be positive and equal to that difference. Yes? I mean, suppose I do this and I get 3 volts. Then that means that the difference in potential between this point and this point is 3 volts. But because this is 0, this has to be 3. Right? But it's not 3 volts, I don't know what it is. But if I were you, I would keep a few more decimal places to this and only at the end do the rounding up. So whatever you get, this looks like 6.78 times 10 to the 3. Something like that. I think, is that right?
Yeah, that's right.
Yeah, so then the potential there, V1, let's say, the potential at this point is going to be that. Because this would be like V1 minus V